to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because it's open mic. Okay, let's move right along now to the first listener phone call.
The thought-provoking question I would like to ask would be, what if you could theoretically travel the speed of light towards an object? I know that it would be blue-shifted, but how would it be perceived by the person or object traveling towards it?
Well, you're absolutely right. If an object moves toward you, light is blue-shifted. So let me explain. Let's say you're a cop, and you're looking at motorists that are speeding by, and you have a laser beam that can track the velocity of these cars. Now, how do you do it? How does your car, your cop car, determine the velocity of a car speeding by? Well, it shoots a laser beam, and the laser beam goes back to the police car. And when red light goes toward you, it is compressed. Light is a wave. And when this wave, like an accordion, moves toward you, it's compressed a little bit. And instead of being slightly reddish, it turns slightly yellowish. And eventually, if it goes fast enough, bluish. That's called the blue shift. So when a yellow star moves toward you, it becomes bluish. Not by much, but enough that you can measure it. When a yellow star moves away from you, it turns reddish. Now, when we do this in outer space, we look at the Doppler shift, not of speeding cars by a cop car, but looking at galaxies and stars, where we find a red shift, meaning that the universe is expanding. Now, our questioner asks a different question. What happens if you are in the car being analyzed by the police? A laser beam shines onto your car and bounces back to the police car, calculating your velocity. The greater the blue shift, the faster you're moving until, bingo, you get a speeding ticket. So the question is, if you're now in the car, watching the laser beam hit your car, what do you see? Well, the laser beam also is blue shifted. So the laser beam coming at you is compressed, and therefore the laser beam is also blue shifted as it reaches your car. So you have two blue shifts. The cop car detects a blue shift and uses that to calculate your velocity and give you a speeding ticket. If you are in the car, you will also see a blue shift as the laser light hits your car. So, something as common as a Doppler shift is used in radar, where we calculate the velocity of rockets and airplanes, and also the velocity of the expanding universe. Okay, let's move right along now to the next listener phone call.
Hi, Michio. This is RK. I had a question for you on an AMA Reddit you did a short time ago, and you skipped my question. The question is, how is it possible to conserve such extreme amounts and degrees of angular momentum in singularities that are in the amount of billions of solar masses only in the context of space-time? I just don't see how it's possible.
Well, first of all, you're absolutely right. We see black holes that weigh millions, billions of times the mass of our sun, lurking at the center of galaxies. Now, if you want to see a gigantic supermassive black hole tonight, go outside, look in the direction of Sagittarius, and you can do that on your cell phone. Download an app on your cell phone that allows you to see the night sky with all the constellation laid out for you. You can do that. Think about it. A planetarium right in your cell phone as you go outside. Download the app, and you can see all the stars with all their names laid out for you as you gaze into the stars. Now, go in the direction of Sagittarius. In Sagittarius, an area called Sagittarius A, there is a raging black hole. It weighs roughly 2 million times the mass of our sun. Incredible. 2 million times the mass of our sun. Now, normally, Sagittarius should be lit up like a Christmas tree. It is the galactic center. We should see a fireball. That's right. Every night, by rights, you should see a fireball corresponding to the center of the Milky Way. But what do you see? Almost nothing, because of dust clouds. The Milky Way galaxy is dusty, and that's why, unfortunately, this gigantic flaming ball of fire looks black. And in the center of it is a black hole. Now, it's spinning, as you correctly pointed out. In fact, it's spinning, we see many of these black holes spinning at about 1 million miles an hour. You can actually clock these things as they go spinning, because these black holes are the remnants of a condensed ball of gas. Now, you know that in an ice rink, when a figure skater brings in his or her arms, they speed up. Okay, well, let's move right along now to the next listener phone call.
Dr. Kaku, this is Patty Harada. This is my question. I get it that we are all stardust. I am plagued by a confusion that is deeply significant in my understanding of that fact. So let's take mammals as an example. We're saying that are we saying that which is created in the womb, for example, is also stardust? Are we saying that stardust creates more stardust? That's my question, and it's probably not as thought-provoking as what you're looking for, but I sure would like an answer. Thank you. I admire you so much. I'm glad you are there. Bye.
Well, thank you. And first of all, you're absolutely right. We are made out of stardust. When you look at your hands and you look at your feet and your body, and you ask the question, where did it all come from? I mean, before you were born, before your parents were born, where did all the atoms of your body come from? And they came from the sun. In fact, even before the sun, there was a supernova, an exploding star, which created many of the higher elements. So a star is an oven. It takes hydrogen, fuses hydrogen to create helium. Helium is a byproduct of the burning process of hydrogen. Then you heat up helium, and what do you get? Lithium, beryllium, the higher elements. So slowly you cook from hydrogen to helium to lithium over billions of years. The star eventually explodes, seeding the galaxy. And then out of the seeding comes the next generation of stars. So our sun is perhaps a second or third generation star. And when stars explode, they create other stars which condense, and out of the condensation of these stars comes the solar plane, the ecliptic plane, and out of the ecliptic plane come planets. And out of the planets you get mountains, and out of the mountains and oceans, especially the oceans, eventually you get DNA. Now, some people think that when we say that we are made out of stardust, then by magic, stardust suddenly turns into us. Or stardust, just like in the old Peter Pan movies, stardust is a magic thing you can whip into any substance you want. No, that's not how it works. When we say that we're made out of stardust, all it means is that originally, where did the hydrogen come from? It came from the interior of stars, which burn the hydrogen to create helium. Helium burns to create lithium. It burns to create beryllium, and on the way up the periodic chart. So that kind of stardust, we're talking about gas. Gaseous material in the early solar system, out of which planets condensed. And when planets condense, we got mountains and oceans. And in the oceans, DNA got off the ground. So it's not so simple as saying that, bingo, stardust turns into people. No. Stardust turns into planets. Planets have mountains and oceans, and we came out of the oceans roughly 3.5 billion years ago. Out of the oceans, the first DNA got formed, and the DNA could replicate, and that's why DNA eventually began to populate the oceans. Okay, well, let's move right on to the next listener phone call.
Hello, Dr. Kaku. I'm a medical student at Frank H. Nutter School of Medicine in North Haven, Connecticut. And my question for you is related to evolution and how it relates to technology. Biological organisms depend on the genetic code of RNA and DNA, but they also depend on ribosomes, which use the information of RNA and physical processes to produce proteins essential for life. And at its core, it's essentially a process of converting recorded information into a physical object. Now, when you think about it, this isn't different from the development of a tool and the creation of modern technology. We're using pre-existing information and physical processes to make machines. So my question, Dr. Kaku, is this. Could we potentially become the equivalent of ribosomes for future intelligent artificial beings? So thank you very much for your time and your contributions to the scientific community. Have a great day.
Well, that's quite a question. First of all, as you know, we are made out of cells. Inside the cell, there's a code that instructs molecules to create copies of themselves. So that's why DNA is so different. What's all the fuss? What's all the fuss about DNA? Well, first, it has a code. The code is a blueprint to create life. But second, and that's more important, second, it reproduces itself. It makes a carbon copy of itself, and that's how we reproduce, and that's why we have humans. And in each reproduction cycle, slight errors and changes are introduced, and that gives us evolution. Now, if DNA is a long strand of chemicals, you have to rearrange it and cut it. Cut it and splice it like you do with toys in order to create more complicated sequences of DNA. So you need a cutting tool by which you can snip DNA and then rearrange it, patch it together. So, for example, you have 50% of your DNA from your mother, 50% of your DNA from your father, and it's also spliced together by cutting tools, and these cutting tools are the ribosomes. So the ribosomes have within them the ability to cut DNA, splice them together to create more complicated sequences of DNA, and that allows DNA to reproduce. And that's why we can have children. That's why we have evolution, because there are mistakes introduced in every generation of replication. Now, you ask an even deeper question. What happens if we do this with robots? Can we have artificially intelligent robots? A key thing about DNA is that it reproduces itself. Now, then the question is, can robots reproduce themselves? Is that a possibility? Well, it turns out that mathematicians have actually asked this question. There was a famous mathematician, John von Neumann, one of the great mathematicians of the 20th century. He discovered game theory. He helped to build the hydrogen bomb. He explored many new branches of mathematics. And he asked himself the question, can you build a robot which, like DNA, will reproduce itself? In other words, does it have ribosomes by which you can splice together a code to create artificially intelligent robots that can reproduce themselves? Well, he started with a simple algorithm. Let's say I have a bunch of Tinker Toys that you buy in any shop or any kind of toys that you can splice together. So the splicing together is done by the ribosomes. And you have all these different kinds of Tinker Toys, let's say 4 or 5 different types, and then you try to write a mathematical rule. Let's splice 2 Tinker Toys together to get a third Tinker Toy. Well, this is a mathematics problem. How complicated can you get? Well, he found out that very rapidly you can create incredibly complicated objects, but the mathematics was so horrendous, he gave up. And so even today, people are still struggling with the question of writing down the mathematics of self-reproduction. Now, we know it's possible because, of course, ribosomes do it. Ribosomes cut DNA, splice them together to rearrange them to create you and me. But can robots do that? Well, that we're not sure. However, it is practical because NASA wants to put self-replicating robots on the moon. Now, think about it for a moment. It takes an enormous amount of money to put a pound of anything on the moon, about $100,000. $100,000 to put a pound of anything on the moon. But if that 1 pound of junk on the moon is self-replicating, a robot that can reproduce itself, you could save billions of dollars. Just think about that. One little piece of robot that can reproduce itself. back to Science Fantastic with Professor Michio Kaku. If you want to be part of the March of Science, then give us a call. Why should we scientists have all the fun working out the laws and mysteries of nature? Why don't you jump in? Give us a call at 612-564-8135. And you can have your thoughts heard on national radio. So, for example, many people say that, well, my question is kind of dumb, but if you have a dumb question, chances are a lot of other people have had that exact same question. And maybe they're not so dumb, because sometimes the dumbest questions are the most profound questions of all. As I mentioned before, years ago, there was a 16-year-old boy who asked a stupid question. The 16-year-old boy said, can you outrace a light beam? Very simple question. Can you run so fast you can go and outrace a light beam? It took him 10 years to figure it out. He finally learned the laws of light at the university, got his PhD, and when he was 26 years old, he found the answer. And the answer is no. You cannot outrace a light beam because the speed of light is the ultimate velocity in the universe. His name was Albert Einstein. So from such a stupid question came relativity, which makes possible the energy of the stars, the energy of the sun, the energy of an atomic bomb, the wonders that you see in your living room with lasers and transistors and computers. A lot of it comes from the work of a man who asked himself a question when he was 16 years old. Can you outrace a light beam? Okay, so if you want to get on Science Fantastic, give us a call at 612-564-8135. Let's go on to the next listener phone call.
Hi, my question is, who should be responsible for the course of society in the future? For instance, a human or an AI? Who could protect us best?
Well, I didn't quite get your question, but I think what you're asking is the relationship between humans and AI in the future, and what will be the relationship far in the future. Well, we had this debate between two billionaires, Elon Musk and Mark Zuckerberg. Mark Zuckerberg of Facebook says that AI is going to be useful, helpful, job creating. We're talking about a new economy based on AI. And then we have Elon Musk of SpaceX and Tesla Motors who says, not so fast, not so fast. There is a downside, because what happens when the robots get so smart that they decide to take over? This is an existential threat to all of humanity. I was on CNN on the Richard Quest show, and Mr. Quest asked me that question. Who's right, Zuckerberg or Musk? And my attitude was, well, neither. In the short term, Zuckerberg is right. For the next coming decades, new billionaires are going to be minted. New industries, new creative value will be generated by artificial intelligence, a new renaissance. But in the long term, let's not be stupid. In the long term, let's not be naive about this. Yes, robots could become more intelligent to the point that they become a threat to us. However, right now, robots are as intelligent as a cockroach. They can barely walk across the room. They can barely recognize objects. But sooner or later, they'll be as smart as a mouse, then a rat, then a rabbit, then a dog and a cat and a monkey. At that point, yes, they could be a threat to us. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, in the end of February, I'll be on a book tour. Go to my website, mkaku.org, mkaku.org. Maybe I'll be signing your copy of my latest book, The Future of Humanity. What will humanity look like 100, 500, 1,000 years into the future? We're going to be going into outer space. Next year, we're going back to the moon. In a few years, Americans will be walking on the surface of the moon after a 50-year gap. Beyond that, we're going to be walking on Mars. Beyond that, perhaps colonizing the solar system. So what about the future of the human race as we move into the stars? Find out by getting a copy of my book, The Future of Humanity. Go to my website, mkaku.org, for more information. mkaku.org. Okay, let's move right along to the next listener phone call.
My question would be, do black holes play any effect on dark matter? Or does dark matter have any effect on black holes?
Well, you ask a rather embarrassing question because the short answer is we don't know. However, let's define these terms first, and then you can make up your own mind how much we know or don't know about these things. First of all, a black hole is a dead star, a star that has imploded, giving you a mass that is extremely heavy, so heavy that light itself cannot escape. That's why it's a black hole and not a white hole. However, dark matter is a very recent discovery. It turns out that surrounding the galaxy, surrounding the Milky Way galaxy, there's a halo. A halo consists of a new form of matter which holds the galaxy together. I mean, think about that. Every time you see a gorgeous, gorgeous photograph of a galaxy spiraling away, realizing that surrounding it, there's a halo 10 times bigger than the galaxy itself, consisting of a new form of matter out of which we are clueless. We don't know what that matter is made of. In fact, if you ever figure out what dark matter is made of, tell me, and we can split the Nobel Prize. So then, what is the relationship between dark matter and black holes? We don't know. Our galaxy has a black hole at the very center, which weighs about 2 million times the mass of our sun. Surrounding the galaxy, 100,000 light years away, is this gigantic halo of dark matter. Now, will they interact with each other? In the main, no, because dark matter surrounds the galaxy, while the black hole is at the center of the spiral galaxy. But can dark matter fall into a black hole? And the answer is yes. Anything that has gravity can fall into a black hole. So you're asking a cutting-edge question, a question that at the present time we have no simple answer for. So most astronomers, I think, would say that dark matter surrounds the galaxy, which in turn surrounds the black hole, so they are disjoint. They are not connected to each other. But can dark matter fall into a black hole? And the answer is yes. Okay, let's move right along to the next listener phone call.
Hello. I have a question. I'd like to know what are your thoughts on whether or not black holes could be generating new universes, and I'd like to know what effect do black holes have on the expanse of the universe. My name is Lorenzo Rodriguez. Thank you for your time.
Well, you ask a very interesting question because, yes, there are some physicists who believe that galaxies give rise to baby universes, and that perhaps that's the reason why we live in the universe that we do, because there are a lot of baby universes out there. Now, you may say to yourself, well, that sounds like it's nuts, but it turns out that you can't rule it out. So let me begin. You see, a black hole is a region where space itself begins to rip. So if you fall into a black hole, what happens? Well, the short answer is we don't know. No one's ever done it. We have no measurements. However, the pure mathematics of black holes says that you fall through it and you fall out of it on the other side of the universe, in a white hole. So black hole is on one side, matter falls in, matter falls out the other side in a white hole. So black holes are in some sense gateways to other universes. So if you fall into a black hole, you don't necessarily get crushed to death. You simply come out the other end in a white hole. So in other words, black holes could connect you to baby universes. There could be lots of baby universes connected to our universe. Now, there are some physicists who believe that you could have evolution, a la Darwin, on the scale of universes. The universes which dominate are the ones which have lots of babies, lots of black holes to create lots of baby universes. Those are the universes which dominate because they have the most babies. Therefore, our universe should be one of them. So perhaps the reason why our universe is the way it is because our universe won the cosmic jackpot. Welcome back to Science Fantastic with Professor Michio Kaku. Okay, well, let's move right along to the next listener phone call.
Hello. I was just thinking that it's possible that the Planck length is the smallest distance that we can theoretically measure, and the speed of light is the constant, the most swift-moving thing in the universe, then the amount of time that it takes light to travel the Planck distance, is that not the tiniest measurable amount of time that we could ever conceive of? Would that not be the basis of the shortest instance? If nothing can change over the distance of the Planck length in a specific amount of time, then, well, what could happen? The universe couldn't change in anything shorter than that. So what do you think about that?
Well, you ask a question that is one of the deepest of all questions, and that is, what is the fundamental length, the fundamental particle, the fundamental object out of which the universe is created? Now, the Greeks were the first to ask this question. In fact, Zeno was a philosopher who made a paradox out of it. Zeno asked the question, if you walk across the river, you have to go through the midpoint of the river. But to reach the midpoint of the river, you have to also go through a point midway to the midway. That is 1/4 of the distance. In order to go 1/4 of the distance, you have to go 1/8 of the distance. ... Since there are an infinite number of points in a line, it takes an infinite amount of time to go through an infinite amount of points. Therefore, you cannot move. This was incredible. Here was a paradox that simply said motion is impossible, because motion means you have to go through an infinite number of points. Since it takes an infinite amount of time to go through an infinite number of points, motion is not possible. Well, obviously, there's something wrong with that paradox, because motion is possible. Who finally solved it? Well, Newton came very close, because Newton divided intervals up to very small pieces, but he said that it takes an infinitesimal amount of time to go over an infinitesimal distance, and it adds up to a finite number. That is called calculus. When you take Math 1 in college, you are reproducing Zeno's paradox all over again. Well, now, physics asks another question. What is the smallest particle? You can smash a proton apart. A proton is roughly 10 to the minus 13 or so centimeters across. But what's inside a proton? Well, inside the proton there are quarks. But what's inside a quark? And so some people think in something called the onion theory. The onion theory says that there are infinite layers of onions. Every time you peel away one layer of an onion, you get another layer. One layer, you have galaxies. You peel them away, you get stars and solar systems. You peel them away, you get planets. Peel them away, you get mountains and oceans. Peel them away, and you start to get organisms like you and me. You peel that away, you start to get molecules. You peel that away, you get atoms. You peel that away, you get protons. You peel that away, you get quarks. And the next question is, what lies beyond the quarks? Does it stop? Well, we think it does stop at something called the Planck length, which you correctly pointed out. It was Max Planck himself, the creator of the quantum theory, who asked himself a simple question. What is the smallest distance? Using pure mathematics, he came out with the Planck length. Now, you ask a question. If a light beam were to go across the Planck length, how long would it take? And the answer to that is Planck time. We think that the smallest particle known is actually a string. And the string is the Planck length in terms of size. So we think it stops. We're not sure. But we think ultimately there is the smallest distance, and that distance is the Planck length. The Planck time is the amount of time it takes to go across that distance. How big is it? 10 to the minus 33 centimeters. An incredibly small distance, but it is a distance, we think, of the Big Bang. We think the Big Bang was created because of a singularity the size of 10 to the minus 33 centimeters. Can we prove it? No. At the present time, we physicists are still debating this question. What is the smallest length? The leading theory, the theory that I believe in, is string theory. String theory says the smallest distance is the size of a string, 10 to the minus 33 centimeters. Now, to prove that requires energy. How much energy does it take to probe the Planck length? 10 to the 19 billion electron volts. That is a number beyond human imagination. It is, in fact, the energy of the Big Bang. So if you understand Zeno's paradox, then you understand the smallest distance. And from the smallest distance, you can get the energy associated with that smallest distance. And what is that energy? The energy of creation. The energy of the Big Bang itself. Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, the lines are open. That's right, open mic on Science Fantastic. Okay, well, let's move right along to the first listener phone call.
My question is, because our universe is suitable for life as we know it, and we can observe it, but provided string theory is right and there are a multitude of universes, would it be possible for us to exist in observe universes that don't operate within the same physical laws as our own?
Well, you ask a very interesting question because string theory does have some detractors, and let me explain. First of all, I work in string theory. I'm one of the founders of string field theory, which is one of the main branches of string theory. String theory makes the claim that it is the final theory, the ultimate theory that eluded Einstein for the last 30 years of his life. So what do the critics say? The critics say that, well, string theory is incredible. It unifies gravity with the standard model, that is, unifies relativity with the quantum theory. That is one of the great mysteries in all of physics. But it's too successful. Not only does it predict our universe, but it predicts a multiverse of universes. Each universe is a solution of string theory. Now, if you think about it, that's not so unusual, because take any theory, Maxwell's theory of light, a theory of electricity. How many solutions are there of these equations? Well, obviously, an infinite number. You can have light bulbs, lightning bolts, you can have sparks, you can have all sorts of solutions of the electricity equations. Therefore, it's not surprising that a theory has an infinite number of solutions. But you see, string theory is different. String theory claims to be the theory of everything, the theory of the universe itself. Therefore, each solution of string theory is a universe. So any theory of everything, any theory of the universe also would have an infinite number of solutions, which means parallel universes. Now, the questioner asked the question, what about parallel universes which are quite different from ours? Like, for example, the proton is not stable. If the proton is not stable, then we all disintegrate into a bunch of electrons and neutrinos, so the whole universe collapses into a gas of free-floating electrons and neutrinos. Not very interesting. And then the questioner asks the final question, can we survive? Can we live in one of these alternate universes? Well, for the most part, no. Because in many of these universes, the protons are not stable, so our bodies would begin to disintegrate. But of course, there are also solutions that look just like our universe. And this freaks people out. I mean, think about it for a moment. A universe that looks just like our universe, but there's a twist. Something is different in that universe. Maybe you went to a different college. Maybe you went to a different occupation. Maybe you married someone different. Everything's the same except for one twist. Is that also possible? And the answer is yes. And it's rather spooky, but realize that people who are dead in one universe could be alive in another universe. Now, of course, I'm not saying that ghosts exist. However, it is possible that you could have somebody who's alive in one universe and is dead in another universe. Now, what's the catch? The catch is you cannot move freely between these universes. String theory says that yes, there could be an infinite number of universes out there, but it is extremely difficult to move between these other universes. And if you want to know how to do that, get a copy of my earlier book, Parallel Worlds, where I discuss that very same question. Okay, well, let's move right along to the next listener phone call.
Dr. Kaku, scientists now refer to our gut bacteria biome as a tropical rainforest of bacteria. Seeing as how they've evolved symbiotically along with primates, is it possible our gut flora is a driving force of human evolution? Thank you.
Well, you ask a very interesting question because for many a decade, what happens in your gut was rather uninteresting for most scientists. We realized that it was very messy down there because, of course, food has to be digested. All sorts of bacteria live down there because when you poop, of course, it all comes out. And so scientists did not really spend that much time because it was very complicated, very messy, but now we are beginning to look at it, and we're beginning to realize that, like you said, it's like a rainforest, a jungle down there. It's survival of the fittest. So some people think that evolution does not take place on time scales that you can measure, therefore they doubt whether or not evolution is correct. But actually, evolution takes place in your gut. There is a jungle down there in your stomach and in your intestines. Evolution on a brutal scale takes place every single second. It's survival of the fittest. The law of the tooth and claw down there in your stomach. Now, the questioner then asks the next question. If it's a jungle down there, with all sorts of evolution take place, does that drive the evolution of humans? And the answer is, well, not really. Certain things are driven, like, for example, being lactose intolerant. Some people have a hard time digesting milk because our ancestors did not domesticate cows. The domestication of cows took place relatively recently. We didn't really domesticate animals till about 10,000 years ago at the end of the last ice age. Before then, we didn't have cows. We didn't have milk. Then there was no need for lactose to digest milk. However, it was a mutation in our gut, which allowed us to have lactose, which can dissolve sugar, milk sugar. And so, yeah, evolution took place. That's a very obvious piece of evolution that took place within 10,000 years. But the gross evolution of humanity, that is, the ability to walk upright, the ability to have maneuverable thumbs, the ability to have a larger brain. These evolutions, largely gave rise to humanity, but the evolution inside our gut helped it, but did not determine it. So the evolution of our gut made it possible for us to survive on different diets. But the basic structure of the body, that is the brain, the arms, the legs, that architecture took place in the jungle, evolution taking place in the jungle, not the rainforest of our gut. Okay, let's move right along to the next listener phone call.
My question pertains to consciousness and string theory, and since we don't really have a total grasp on consciousness, it also ties in like DMT when you die. Our body releases a bunch of it. Is it just our consciousness leaving us at the time and going to a different parallel string theory universe where in that universe everything was the same except we had survived from an accident? Thank you.
Wow. Well, you ask a question that combines the most advanced physics with questions in theology. Well, let's take a short break, and after the break, we'll try to delve into the question of consciousness and the laws of physics. Welcome back to Science Fantastic with Professor Michio Kaku. If you want to be part of the fun, and it's open mic on Science Fantastic. Well, before the break, we had a call that goes to the heart of theology, the heart of the most advanced physics, and that is the question of consciousness. What happens to our consciousness when we die? Well, the short answer is, I don't know. There are many religions, many philosophies that deal with this question, and some of these philosophies are not provable one way or the other. For example, take a look at reincarnation. Some people believe that when you die, perhaps you come back. Come back as a different kind of animal, different kind of organism. Who knows? But you see, how do you disprove that? how do you prove or disprove reincarnation? Well, you may say to yourself, well, if somebody claims to be reincarnation of Cleopatra, then why don't you simply ask your Cleopatra some simple historical questions? Well, I did that once. I was at a party once where somebody claimed to be the reincarnation of Cleopatra, and I asked her some simple historical questions. She got them all wrong, but then she said something which stumped me. She said, the history books are wrong. How do I know? Because I am the reincarnation of Cleopatra. At that point, I realized that nothing I could say could shake her belief. Nothing. Because this is outside of the boundaries of science. Science deals with things that are testable, reproducible, and falsifiable. Whether or not you're Cleopatra, that is, you have the consciousness of Cleopatra, is not testable. It's not falsifiable, and it's not reproducible. So let's say someone dies and says he went to heaven and came back from heaven. We have many best-selling authors claiming to have near-death experiences, and they talk about what the afterlife looks like if they had a glimpse of it. Well, maybe they did, and maybe they didn't. In other words, there's no definitive proof. And that's the difference between faith and science. Science demands reproducibility. It demands testability, and it demands falsifiability. Faith is faith. Now, the next aspect of your question, which is pretty deep if you think about it, is what is consciousness? Well, this is something that we physicists have grappled with. Einstein grappled with that question of what is consciousness? And there are two ways of looking at that question. In my book, The Future of the Mind, I try to give you a definition of what consciousness is, looking at the brain the same way that a mathematician would. A mathematician trying to build a robot would also ask the same question. What is consciousness in a robot? Well, first of all, it's trying to create a model. All the information coming through your senses, you try to create a model of yourself in space, in time, and also in society. So, for example, an alligator, I think, has some consciousness. Even a plant has some consciousness. I would say that a thermostat has one unit of consciousness. That is, it has one feedback loop. So I give a definition. A definition of consciousness being the sum total of all feedback loops that give you a model of yourself in space, in society, and in time. So a plant would have one unit of consciousness, or actually maybe five, because it can measure humidity, the direction of gravity, the presence of nutrients, but that's about it. A thermostat would have one unit of consciousness. An alligator, I think, would have level 1 consciousness, spatial consciousness. It understands where it's located with respect to food. Then you have mice and wolves that are socially conscious. They have to have manners, social hierarchies. They know their place in the larger scheme of a society of like-minded mice and wolves. But then what about humans? What separates human consciousness from animal consciousness? Well, I say, and this is my own theory, I say what separates us from the animals is time. Animals do not understand time very well. Let's do an experiment. Go home tonight and teach your dog or cat the meaning of tomorrow. Such a simple thing. Teach your pet the meaning of tomorrow. And you'll find out very quickly that they don't understand tomorrow because they don't have memories to speak of. Memories are something that we humans have because we constantly daydream. We constantly run the videotape forwards and backwards and say, what if? What if we only did this? Animals don't do that. Animals live in a world of instinct. So that's one way of looking at consciousness. But then there's another way of looking at consciousness. Because you see, at the very heart of the quantum theory, the theory of atoms, we have a paradox. And that is, quantum theory says, you don't really know where something is until you look at it. The looking at something process determines its existence. Now, Einstein didn't like that. Einstein hated that idea because Einstein thought that objects existed independently of who's looking at it. What should it matter who's looking at a rock? A rock is a rock. independent of who's looking at it. But you see, in quantum mechanics, you have to make a measurement. The rock exists in all possible states. Now, Einstein thought, this is stupid. I mean, all possible states? So you're telling me that a cat, before you look at it, could be dead and alive simultaneously? Well, yeah, that's right. Einstein was wrong in this question. So where does consciousness come in? Well, it turns out that to make a measurement, you have to be conscious. Conscious beings make measurements. Unconscious beings do not make measurements. So all of a sudden, consciousness came in the back door. And quantum mechanics, the theory of atoms, depends on you having consciousness. But then the question is, who determines whether you exist or not? You're the measurer. Who determines whether you exist or not? Well, someone has to look at you. Well, who determines if he exists? Someone has to look at him. And there's an infinite chain, an infinite sequence of consciousness, each conscious being looking at the previous conscious being, leading up to God. Now, you may say to yourself, at this point, this is nuts. This is crazy. You're telling me that quantum mechanics, the ultimate theory of the atom, inevitably yields God? And the answer is, well, yeah, that's one version of quantum mechanics. This is the Eugene Wigner interpretation of quantum mechanics. Eugene Wigner believed in this. He was no fool. He helped to create the atomic bomb. He's one of the founders of the quantum theory, in fact, and he believed that ultimately cosmic consciousness is required to make a measurement. Now, you may say to yourself, well, what do other physicists today believe in? Well, I'll tell you what. My theory, in fact, the theory of most friends that I know, many of them Nobel Prize winners, in fact, believe in the multiverse. That is, in one universe, cats can be dead. In another universe, cats can be alive. And the universe splits in half. So we have a multiverse of universe with universes constantly splitting apart. You don't need consciousness in this formulation. You need a multiverse. Now, to get more information about this, because this is pretty sticky, go to my book, Parallel Worlds, and if you ever figured out the question of consciousness in quantum mechanics, you will win the Nobel Prize in Physics. You will have a branch of physics named after you. That's how deep this problem is. It is one of the deepest paradoxes in all of science, and it's open-ended as to the resolution of this question. Einstein hated all of this, but hey, what can I say? Einstein was wrong. Okay, let's move right along to the next listener phone call.
Yes, I had a scientific question regarding quantum entanglement. The forces behind quantum entanglement, could this actually mean that it's faster than light itself, based on the mysterious properties? That's my question. Thank you.
Well, the answer is yes. Einstein said nothing can go faster than the speed of light, and actually that's not quite correct. There are some things which can go faster than the speed of light. If I have two electrons, and they're vibrating in unison, and then I separate them, according to the quantum theory, an umbilical cord. An umbilical cord emerges that connects the two, like a telegraph wire. And if you jiggle one, then the other one senses the fact that its partner has been jiggled. Well, so far so good. But then the question is, how fast? How fast did that knowledge go between point A to point B? And the answer is, it went infinitely fast. At this point, Einstein said, aha, gotcha. You just said that quantum mechanics, the theory of the atom, predicts that messages can be sent faster than the speed of light. That violates relativity. So who's right? I'll give you a hint. Einstein was wrong. Welcome back to Science Fantastic with Professor Michio Kaku. Once again on Science Fantastic, we take your phone calls. Okay, let's move right along to the next listener phone call.
Hey, good morning. Calling out of Indiana. My name is Michael. My question to you is, in the future, as mankind slowly transitions from actually being human to being more bionic and eventually purely machine, what will be the motivating factor for a civilization of machines to explore? In a civilization of robots look to the sky and wonder and question and be driven to explore? Thanks.
Well, you asked a question that we actually debated on Science Fantastic with a number of our guests. Quite a few of our guests are futurists who look thousands of years into the future. Let's say we meet a civilization 1,000 years ahead of us and they land on the planet Earth. What are they going to look like? Something out of science fiction novels? Not necessarily. They could be robotic. Because after a while, they may say that robot bodies are faster, smarter, and better than ordinary bodies. So why not merge with our robots or become robots ourselves? In which case, are they going to want to explore at all? Won't robots simply get bored exploring the universe? Because that's for humans. And robots may have no interest in this. Well, I have my own point of view. My own point of view is that, well, yes, there's always a possibility that we will become so intelligent that we'll merge with robots, and robots may simply not want to explore the universe. They may do whatever robots do. Well, I take a slightly different position. I believe in something called the caveman principle, or cavewoman principle. You see, our brain and our personalities have not changed much in the last 200,000 years since we emerged from Africa. In other words, we still like the same things that our ancestors liked. We like to be healthy. We like to have the admiration of our peers. We want to be attractive to our peers. We want to have the respect of our peers. So as we become more intelligent, as we have the ability to change ourselves, to genetically modify ourselves, we're not going to modify ourselves to the point where we look goofy and we look like a freak. So all the science fiction novels where people of the future are like brains in a bunch of liquid, and that we're nothing but pure brains hovering in a liquid, I think that is not the future of humanity because of the caveman principle. Who wants to look like that? Who wants to look like that with all these electrodes coming out of your brain? Who wants to look like that? So I think as time goes by in the future, as we have the ability to genetically and mechanically alter ourselves, we're still not going to change much. We'll have the ability to put implants to make ourselves stronger, more intelligent, blah, 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 to become Supermen. But then we'll take them off and act normal again because we don't want to look like a bunch of idiots. Welcome back to Science Fantastic with Professor Michio Kaku. Okay, let's take the next listener phone call.
Hi, I just wanted to record a science question. My name is Nina Tal, and I recently learned that for any mass with a key, there is a de Broglie wavelength associated with it, and the relationship is lambda equals to h over p. But I had just a quick question. So if you have a certain mass that's made up of, many smaller atoms, right? How do you know if you should consider the entire mass of motion to be, just one mass, and then associate one de Broglie wavelength with that, or consider the motion of every individual atom and then consider just this group of waves kind of moving with smaller de Broglie wavelengths than that one large one, where you would consider the mass to be just one entity rather than the sum of many smaller atoms? Thank you.
Okay, well, you ask a question which is actually quite relevant to today's physics. First of all, Einstein introduced the idea that light can have particle and wave-like nature simultaneously. He won the Nobel Prize for that. That's called the photoelectric effect, which is the basis of television. The fact that photons, particles of light, can act like particles or waves. Well, then a young grad student by the name of de Broglie asked the reverse question, and that is, if photons are particles of light that act like waves, then what about electrons? Can matter also wave? Well, that was considered heretical. What? an electron waving. But, yeah, he wrote down his famous equation, which you mentioned, and the de Broglie wavelength gives you a description of electrons as a wave. Now, that upset a lot of people. But he was right. In fact, he won the Nobel Prize. And it turns out that, yes, electrons have a wavelength. And you can use that wavelength to treat them like beams of light. They can be diffracted. For example, in our physics class here at the university, we shoot electrons through a tiny peephole. Tiny peephole. What comes out the other end is a wave-like diffraction pattern, proving that de Broglie was right. And then a guy named Erwin Schrödinger asked himself another question. If an electron is a wave, then what is the wave equation? Waves obey an equation. What is the wave equation for the electron? And so Erwin Schrödinger then wrote down the equation. It's called the Schrödinger equation, which is one of the most important equations in all of quantum physics. In fact, the sum total of quantum physics can be represented as a solution of the Schrödinger wave equation. Now, to understand that equation, you need 3 years of calculus. But for those people in the audience who've taken 3 years of calculus, you can see perhaps the most famous equation in all of quantum physics. Now, E equals mc squared, of course, is the most famous equation in all of physics, but the Schrödinger equation is the second most important equation in all of physics. Now, the question that was asked is, what happens if you combine them? If you combine them, there's two ways to combine waves. One is they can be coherent. They can vibrate in unison. That's called a laser beam. Why are lasers so miraculous, so counterintuitive? Lasers are special forms of light because all the waves are vibrating in lockstep. That's called coherence. So they obey essentially the properties of one gigantic photon, all vibrating in unison at lockstep. That is called coherence. However, decoherence is what you see around you right now. When you look at a light bulb today, light is decohered. All the waves are jumbled up together like a junkyard, vibrating at different frequencies, and that's why you don't see ordinary light acting like a laser beam. Now, the same thing can apply to matter, and that's the question that was asked. Can matter also have this same property? And the answer is yes. Matter can also vibrate in unison. It's very difficult to do that, and that would give you an atomic laser. Not a light laser, but an atom laser, that is an atomic laser. And so it is possible that you can have waves of light vibrating in unison. Now, why should we care? One day, computers of the future will use this effect. Quantum computers rely on this effect. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open. It's open mic. Okay, let's move right along to the next listener phone call.
Hello, this call is for Dr. Michio Kaku regarding the questions on Twitter. My question to you is, if I am approached by a flat earther who genuinely wants to be shown that the world isn't flat, what is the best way for me to relay the observation without condescension and with simplicity? Thank you very much, and have a great day.
Well, yes, believe it or not, there are some people today who believe in the flat earth theory because it seems to agree with experience. Everywhere you look, things look flat. That is, two-dimensional. Therefore, if you want to prove that there is a third dimension, then you have to go up. And when you go up and you look down on the planet Earth, you can then begin to see the curvature of the Earth. Now, if you're in an airplane, you go maybe 35,000 feet or so, and so you're about maybe 7 miles up. 7 miles up, you can just begin to see the curvature of the Earth in an airplane. Better yet is to take a rocket ship where you can clearly see the curvature of the planet Earth. Other than that, These people will never believe what you say, because the only way you can show that there is a third dimension is to move into the third dimension. Another way is by balloons. You can put a camera on a balloon and have the camera send a signal back to your cell phone, and a balloon will go many miles up, and you can see the curvature of the Earth with a camera. And so again, the only way to prove that the Earth is not two-dimensional is to go into the third dimension, that is, go up, either in an airplane, a rocket ship, or on a balloon via a drone camera. Okay, let's take the next listener phone call.
Hello, I was calling to record a science question. My question is, does a spinning object have more gravity than a non-spinning object? Thank you.
Well, at first you may say to yourself that they have the same amount of matter and energy, but actually there is a slight difference. You see, spinning motion is a form of energy, and Einstein says that energy and matter can go back and forth. For example, it's possible for a light beam to turn into a rock, or a rock to turn into a light beam. Now you may say to yourself, well, that's impossible. Well, if that rock is uranium, and that light is the flash of a nuclear weapon, then clearly the rock has turned into energy. So therefore, when you look at the weight of an object, you have to calculate its energy as well and add it to that. And so Einstein says you have to take a look at the matter energy. Matter energy, because matter and energy are really the same thing. They can simply go back and forth between each other. So yes, you have to take into account the spin of an object when you weigh it. By the way, it's very tiny. So for all intents and purposes, you can weigh yourself without having to spin on the scale. Okay, let's move right along to the next listener phone call.
Hello, my name is Jeff Hartman. A few days back, I was thinking about, after listening to a podcast where they're talking about whether humans should send focused beams of electromagnetic radiation to nearby planets or star systems, basically letting the universe know we're here besides the 40-year or 60 years of radiation we've been sending out already. But there was worry because people think aliens might be bad, they could come get us, whatever. And then I got to thinking, for a species to become intelligent, it was hard for me to think of a way that a species can evolve to be intelligent and be evil at the same time. It doesn't add up to me because I think about humans, I think about how to become intelligent. We had to work as a group, nurture, care for one another, and I think that might be something universal. So, if there is a worry about dangerous alien civilizations, I would question whether if that's unnecessary worry. Now, AI, on the other hand, I'm not sure about that, but I'm not sure. I want to hear your thoughts on an intelligent species evolving to become intelligent and being evil. Thank you.
Okay, well, first of all, I do not believe that we should advertise our existence in outer space with radio for precisely the reason that you mentioned, that perhaps the aliens could be dangerous. And then the question is, could they be evil? Well, that's actually not the point, because what happens if the aliens don't care? When we go into the forest and we see ants in an anthill, we don't talk to the ants. What do? We just pave them over. Now, does that mean that we're evil with respect to the ants? Does that mean that we have a grudge against the ants, that we viciously hate the ants? No, we just don't care. Same thing for War of the Worlds. When H.G. Wells talked about the Martians invading us, did the Martians hate us? No, we were in the way. The Martians wanted to take over the Earth because their planet was dying. Our planet was young, fresh. Therefore, we were an obstacle that got in the way. Same thing when we go in the forest. We don't necessarily hate the deer, but we pave over the forest anyway for a housing development. And so it's not a question of we're being evil with respect to the deer and the squirrel. No, we pave them over. because they're in the way. Therefore, I think when we meet intelligent life in outer space, if they're that advanced, yes, there is a possibility that we could be in the way. Now, personally, I believe what you said, that intelligent beings will perhaps not be evil because they'll realize that sentient beings can feel pain and we deserve to survive. But you can't rule it out. You cannot rule out the idea that perhaps we are simply in the way of alien creatures. Well, unfortunately, we've run out of time. This is Science Fantastic.